Okay, we're going to start the first part of Chapter 3, Objective 1. You're going to be introduced to a huge step forward in the history of mathematics. It's called the rectangular coordinate system. It's also called the Cartesian plane. The Cartesian plane, maybe you've heard of, that's not good. Here we go. René Descartes. If you take a philosophy class, you will. Many great philosophers were also mathematicians. Well, he is the one who came up with this, or at least he's known for it. So sometimes the rectangular coordinate system I'm just going to put chord system is also known system is also known as the Cartesian plane after René Descartes. So he's French. Basically, the genius is, before then, mathematicians had pretty much been looking at numbers as they occur anywhere on the number line. That's not much of a picture, but René Descartes decided, well, what happens if I add another number line that intersects our regular number line? Now, this is all fake history. I don't know actually how he came up with the idea, but he adds two number lines, the regular horizontal number line. So we'll call it X, and let's intersect it at right angles with another number line going vertical or up and down. And instead of a number, our numbers will be points. Our points can be anywhere. So suddenly, instead of looking at just one-dimensional objects, we can look at two-dimensional objects. So the beauty of this is that we literally have a visualization of math that we never had before. So right here would be a point, and each point has an address. So I'm going to show you a better picture of this later on. So basically I'm drawing a line. So this horizontal line right here is called the x-axis. And the vertical line is called the y-axis. And these are points. They're literally zero-dimension objects. But each point has an address, and that address is given by an x value and a y value. Together, the address is called an ordered pair. Think if you were to live in a city where the streets run east and west and north and south, and your address is given by some east direction or west direction and some north or south direction. So in this case, the value of x, given a point, you just go down, and then you measure over from the very intersection right here. You measure over, and that's going to give you a value. Say in this case that value is 5. You do the same thing to the y-axis. You measure down where it intersects. It's going to intersect at a right angle. I didn't draw that completely straight. And suppose the distance is 6. So in this case, xy would be expressed as 5 and 6. But it's not just the distance, but it's going to be the distance with signs. So let's go back to our overview. This has got it a little bit better. So here, notice this is the ordered pair, 3, 5. There's the point. There's the x-axis. Notice the x-axis here, we're actually dividing it into little bitty. These ticks right here, they just help us know the values of x at right there. But we start with 0, 5, 10, etc. Then going to the left, just like the number line, -5, -10, etc. Here's the x-axis. Here's the y-axis. Where they intersect is called the origin. Now, a point value, they put here a p, that's sometimes you put it there, or sometimes not. Its only function is to tell you this is a point. So we normally don't put them there. Normally we just write an ordered pair, 0, 0. So this point right here has the address that x is 3, so 1, 2, 3, and that the y is 5, 1, 2, 3, 4, 5. The point right there where the two intersect is a special point. It's called an origin. And we can divide the Cartesian plane into 4 quadrants. The quadrants do not include the boundaries. The quadrants do not include the x and the y-axis. So this point here, 3, 5, is in quadrant 1. A point over here would be in quadrant 2. A point over here would be in quadrant 3. And a point down here would be quadrant 4. If I literally could put a point right there on the x-axis, we would say the point lies on the x-axis. If I have a point up here that lies on the y-axis, or down here, we say the point lies on the y-axis. It's the straddling point between, in this case down here, the 3rd and the 4th quadrant. So you start here, and you start moving counterclockwise. If you look here, all of our values of our coordinate entries, our ordered pair entries, x, y, will all be positive. Here, the x values will be negative, the y values are positive. Down here, the x values are negative, and the y values are negative. Here, the x values will be positive, the y values will be negative. The point right there where the two coordinate axes intersect is called the origin, and it has address 0, 0. So we went over the x-axis, we went over the y-axis. An ordered pair in general is just, an ordered pair just has the form x, y. And two ordered pairs x1 and y1, where x is not necessarily equal to x sub 1 and y is not necessarily equal to y sub 1, they're the same if and only if the x values are exactly the same and the y values are exactly the same. So the point determined by 3, 0 is exactly the same as the point determined by 21/7 and 0. The point given by 4 and 5 is not the same as the point given by 4 and 6. They have different addresses. So I have a feeling a lot of you are familiar with this, so I'm not going to go into great detail more because it's going to be clear when we look at the examples. So let's actually do this exercise, exercise 2. We're going to plot each ordered pair, and we're also going to name the quadrant in which each ordered pair lies. So for that, I actually pasted in a clip so I can write on it. So what I'll do is, let me choose maybe the dark blue. and I'll write the quadrant over the point. So this point has address, the x value is 2 and the y value is -1. So this is my x-axis down here. Although these go on and on forever, that's my y-axis there. So I go to my x-axis and I find my 2. And I don't like this one because here is -2 here, which means this is going to be -1. So I'll just write it there. We don't really have a line coming over. We come down 2 and -1, and right there that point is. As a matter of fact, I like this so much now, I'm going to do it a different way. I should change my image so that literally have 0, -1, -2, -4, because -1 is just kind of right in the middle of a space. So let's do it this way. I have another option. So here's what we want to do. I'm going to go into what's called Algebra. And right here you can see the points. 0, 1, 2, 3. So let us actually do our first point, and our first point turned out to be, what was it? 2 and -1. So 2, right here is my 2, and then I'm going to come down on that line until I hit a -1, and then I'm going to put a point right there. That point A has, I put it in the wrong place, 2 and -1. Yeah, here we go. Better. And now you can see here that my point A has the coordinates 2, -1. And this is the first coordinate, second coordinate, third coordinate, fourth coordinate. Erase that. First quadrant, second quadrant, third quadrant, and fourth quadrant. So A lies in the fourth quadrant. So now let's do 0 and 5. So our x value is 0. So here's my x-axis right here. So my x value is 0, but my y value is 5. So I have to go up and find 5, and it's going to, sorry about that. Got to do some moving here. I'll just delete it. So it's 0, 5. So right there is 0 on my x-axis, and then I move straight up vertically to my 5, and I put a point there, and right there I have 0.05. What quadrant does it lie? Not 1, not 2, not 3 or 4. Point B lies on the y-axis. Now we want to do -3 and 5. So again, we look at and we find -3, and then we go straight up 5 units, and there we have -3 and 5. And the last one, so -3 and 5, this is quadrant A, sorry, this is quadrant 1, this is quadrant 2, so C lies in quadrant 2. Now let's do -2 and 0. So here we find -2 on the x-axis, and we're at 0 on the y-axis. So this point right here is -2 and 0. It's not in any quadrant. It lies on the x-axis. And then the final point we're asked to graph is -1/2 and -4. So here is 1, here is -1. So halfway in between 1 and -1 is 1/2, and we want to go down to 4. So I'm going to have to scoot it up a little bit more. So 1 half, 1 half, 1 half, 1 half, right there. I'm not for sure if I'm getting it exactly right. Almost. Let's go ahead and change it. It was really, really close. And it's not quite 4. Sorry, minus 4. It is now. So I had to slightly shift it. So that is minus 1 half, which is minus 0.5, and minus 4. And it also lies in not quadrant 1 or quadrant 2, but in quadrant 3. Okay. So now I'm going to introduce you to a brand new concept in that takes up memory. I don't want to deal with it. We've been looking at linear equations in one variable, usually the variable x. You're going to be introduced to a linear equation in 2 variables, and right here it is. It's 3 times x minus y is equal to 12. So let's take a look at that. And it's got to adjust here. So here is a linear equation in the variables x and y. That's going to be occupying us for quite a bit of this course and the next course. So 3x minus y is equal to 12. And just like a regular equation, any value of x together with any value of y that will make this a true equation or a true statement is considered a solution. So if I say let's let x be equal to 4 and y be equal to 0, then I get 3 times 4 minus 0, which is equal to 12 minus 0, which is equal to 0. So when x is equal to 4 and y is equal to 3, then those values are a solution to this particular linear equation. But isn't there a better way to manifest this information? Sure. I have an ordered pair whose first address is x and the second address is y. So the ordered pair where x is equal to 4 and y is equal to 0 satisfies this equation. So we say the ordered pair satisfies the equation, but the new thing that we've been given by introducing the Cartesian plane is we can say this point lies on the, here we go, line given by the equation three x minus y is equal to 12. We're going to work up to this. In particular, you know what a line is, and it's going to not change its shape in any form in this class, but we will actually be able to graphically think about algebra. Descartes allows us to visualize algebra. He's often called the one single mathematician who algebratized geometry. So geometric figures, for example, like a circle, can now be expressed completely algebraically. So let's go back to what we were asked to do here. We're given the equation 3x minus y is equal to 12. And then we're given several ordered pairs. Remember, each one of these gives us a value of x and the value of y. In other words, for this one, I have x is equal to 0, y is equal to minus 12, because the generic ordered pair is x comma y. So all we're going to do is take each ordered pair in turn, and we're going to plug in the values to see if we get a true equation. So let's plug in 0 for x and minus 12 for y. Notice that the value of y is minus 12. It doesn't get to use the minus that is already there. Y has to bring its own negative with it. So this is the same as 0 plus 12, and that's equal to 12, and that's what the equation says it is. So this one is an ordered pair solution. Let's check another one. So let's check 1 and 9. So 3 times 1 minus 9 is equal to 3 minus 9 is equal to minus 6. But minus 6 is not equal to 12. This says it's going to be 12, but it's not. It's equal to minus 6. So this is not a solution. Let's do another one. Or if you want to stop and pause and do the remaining two on your own, of course, be my guest. The next one we're going to check is 2 and minus 6. Remember, the minus lies on the y value, and it has to bring its minus with it. So I have 3. The value of x is 2 minus y has to bring its negative. So 3 times 2 is 6. Minus a minus 6 is plus 6. And 6 plus 6 is 12. So this one is a solution. So 2 of them were a solution, and the other 2 were not. So now let's introduce formally the main object of our study in all of Chapter 3. It's a linear equation in two variables. So it's an equation that can be written in the form ax plus by is equal to c, where a and b are not both 0. One of them can be 0, but they both cannot be 0. And this particular form right here is often called the standard form of a linear equation. A, b, and c clearly are real numbers. Our x and y are our variables. So this is a linear equation in two variables. Not one, two variables, and that makes all the difference in the world. Here's another concept that is being defined. The graph of an equation in the variables x, y, any equation in the variables x and y, is the set of all points x, y that make the equation true. So guess what? The graph of a linear equation looks like a line. And there's other types of graphs of other equations, but the graph of a linear equation is always the graph of a straight line. So here we've got to determine whether the following equations are linear equations, and we're going to do it by converting them to standard form. We're going to take this as true. There is no proof given, but we're going to simply say a linear equation, by definition, can be converted to this form, and we won't worry about looking at its graph or anything else. We'll just take it for granted that the graph of an equation that is linear is always a straight line. But we're going to determine this by converting them into standard form. So we want to convert them to ax plus by is equal to c for some value c. So let's do it. So we are given, this is 2a, we are given y is equal to 7/3 x minus 15. What we want is ax plus by is equal to c. Notice that the plus right here does not mean b is positive, because remember 7 minus 3 is the same exact thing as writing 7 plus minus 3. So really, addition and subtraction all amount to the same thing when some of our numbers are allowed to be negative. So I want the constant c. The constant is what does not have a variable attached on one side by itself. So I'm just going to leave it on this side. It doesn't really matter that it's on the right hand side, because this is equivalent to c is equal to ax plus by, but it's over there. Let's leave it there. The y is on the right side, so I need to move the 7/3 x term over. When I do so, it becomes negative, and I'm adding that to y. So in this case, this is ax plus 1y is equal to minus 15. So we see that this is a linear equation in the variables x and y. Let's skip and do 2c because they're right side by side. So y is equal to 1 over 2x plus 4. I'm pretty much done. Notice that the 2x is in the denominator of a fraction, and there's nothing I can do to put it up into the numerator. So there is nothing I can do to convert this to ax, where x is x over 1, a is a over 1, those are the same, where x is the numerator of a fraction. So this is not linear. It has a very interesting graph, but linearity is not a property it has. Let's do B and D. To B. So y minus 12 is equal to 3 times x minus 5. So the first thing we're going to do is simplify. So y minus a minus 12 is the same as y plus 12. And on the right hand side we have to use distribution. So 3 times x is 3x. 3 times minus 5 is minus 15. So I'm going to move my 12 to this side over here. I always like to do at least one problem really broken down. I'm going to combine like terms. Minus 15 minus 12 is minus 27. And now I'm going to bring my 3x term over here. It changes sign. Since y doesn't have a negative in front of it, I put a positive in front of it. So minus 3x plus y is equal to 27. ax plus by is equal to c. Well, that gives me a is equal to minus 3. It's the coefficient to the x term. B is equal to 1. That's the coefficient to the y term. And my c term is minus 27. And let's look at our final one, number D. Again, an interesting example. So I have y plus 1 is equal to 3x times x minus 5. So that gives me y plus 1. So again, I'm going to use distribution. 3x times x, 3x times minus 5. So 3x times x is 3 times x. So that's 3x squared. And 3x minus 5, well, 3 times minus 5 is minus 15 times x. Well, we can stop right now because this is a degree 2 equation. By that I mean that when I look at the variable term, I have a variable with an exponent that is equal to 2. And linear equations are always degree 1 equations, and there is no algebraic trickery I can do that will convert this into a linear equation. So, not linear. Our conclusion is not linear. It's an important equation, and you'll be seeing some of that later on, but it's not a linear equation. So here we have some actual already applications of this. So a salesperson is paid monthly $3,000 base plus 20% commission, which is the same as 1/5 of sales. If we let x represent the number of sales, then the monthly pay y is given by equation y is equal to 3,000 plus 1/5 x. Use this information to answer the following questions. So it's not as bad as you might be dreading. So we have an equation. Y is equal to 3,000 plus 1/5 x. Is that linear? Yeah, because it can be written as, we're given y is equal to 3,000 plus 1/5 x. Well, if I move my 1/5 x over, it becomes minus 1/5 x. The y stays put. And there I have it, ax plus by is equal to c, where a is equal to minus 1/5. b again is the coefficient to y, and it's 1, and c is equal to 3,000. So yes, linear. The answer to A is linear. So now let's do something else. If the salesperson sells $8,000 of products in a particular month, what is the salary for that month? So here we have the salary is given by the equation. Y is the salary. Monthly salary. So y is equal to 3,000 plus 1/5 times x. But he sells $8,000 worth of products. So x is equal to 8,000. So let's find out how much he's going to get. Y is equal to 3,000 plus 1/5 times 80,000. No, sorry, 8,000. Well, notice 1/5 times 8,000 is 8,000 divided by 5. So this is something you should not be grabbing your calculator to do. Some of you are really calculator dependent. I saw it on the exam. And it will not serve you at all to keep that calculator dependency as soon as we go back to real classes. So let's go ahead and quickly find out this. 5 will go into 8 one time. That's 3. 5 will go into 36 times. Bring down my 0. Bring down my 0. So this is super simple. I know it's done faster with the calculator, that you won't have calculator access when we go back to live classes. And I really don't want you to have them too much when we're taking exams. So his total take-home pay after a month, literally, I mean, some of you would grab a calculator to add those two together. And that's just becoming too calculator dependent. It's $4,600. So if you think about that, this is really an important equation right here, because some of you will eventually get a job in sales, and you can budget and you say, okay, I need so much a month to live on. How much in sales, given my commission and my base pay, will I have to actually sell to make budget? And if this case, if your budget was $4,600 a month, which is, I mean, it depends on it. If you got a family, that's not anything. By the time you have Algebra, insurance, all of that, just depends. It really just depends. For a lot of you, that's quite a bit a month, because you're still students. But then you would actually know, okay, well, if I can sell $8,000 worth of product a month, I can make my budget. And then the next question is, how difficult do I think it is going to be able to sell $8,000 worth of this? How much does each item cost? Is that one car? Is that 5 cars a month? Is there a market for this, etc.? I think there's one more question. Oh yeah, here, this is a good one. So if the salesperson wants to make more than $5,000 a month, then what is the minimum dollars worth of products they must sell? So let's translate this into the equation. So the relationship given is Y is how much he wants to make. And he wants to make $5,000 a month. He has to make at least $5,000 a month. He could make more, right? So $5,000 is going to be less than or equal to how much he actually makes a month, which is $3,000 in base pay plus the amount of sales you make in dollars divided by 5. So let's go ahead and solve for x. 5,000 minus 3,000 is less than or equal to 1/5 times x. So 5,000 minus 3,000 is 2,000. That's less than or equal to 1/5 x. So what do we do to solve for x? We clear the denominator at the very last step if we want to. We multiply both sides by 5. So 5 times 2,000 is less than or equal to 5 times 1/5 x. So 10,000 is less than or equal to x. So if x, remember, is the amount of sales you make a month. So if your amount of sales is greater than or equal to $10,000, then your take home is going to be $5,000. So not so bad. Okay, so our next goal is going to be to graph an equation. So we're going to be graphing linear equations. And we know they're linear because I just told you so, and that's the subject here. And you can look at each one of these equations. Right there's one, right there's the next, and right there's the next. But we're going to do so by knowing something about a line. So let me go back over to GeoGebra. Let me turn off these points or just delete them altogether. So here is one single point, and there is a line going through that single point A. How many different lines can go through this point? An infinite number of lines. Each revolution of this line is a different line. So how many other points do I have to have a unique single line? Well, if I fix another point and make the line go through 2 points, then I have a unique line. So the saying goes, 2 points determine a line. And that's exactly what we're going to do here, but we're going to do something just a little bit more. Since it's very possible that you can make errors, we're going to actually plot 3 points. We're going to plot 3 points, and then we're going to draw a line through them. And if our line does not go through all 3 points, that means we've made an error. So you say, well, what do you mean when you say plot 3 points? Well, here we go. So let's look at the very first equation. We have an equation that says y is equal to minus 2x plus 3. So what we always do in this equation is we make a table of values of x and y, and I want 3 different values. We're gonna do it 3 different values. Here is x and here is y. But y is equal to minus 2x plus 3. So here you get to choose. You get to choose any values you want for x. So one value you always want to choose is 0. And another value, there's a minus in there. Another value you might want to choose is 1, and another value you might want to choose is 2. So this is called a table of values. So remember, my first column is an x column, and my second column is a y column. So literally, I'm finding ordered pairs x and y. So the first way to do this is take our original equation, y, and that's whose value we're seeking, and we're going to plug in 0 for x. So y is equal to minus 2 times 0, which is 0, plus 3. So my y value in this case is 3. So the takeaway is my first point is 0, 3. Okay, let's do it for my next chosen point. Y is equal to minus 2 times x, which is 1, plus 3. Well, that's equal to minus 2 plus 3, which is equal to 1. So y is equal to 1. So that gives me another point, 1 and 1. And I said 2 points make up a line, but we always want to check. So I'm actually going to do another point. So my last point chosen is 2. So y is equal to minus 2 times 2 plus 3. So that's equal to minus 4 plus 3. So that's equal to minus 1. So my third point is 2 and minus 1. So let me jot these down because I'm going to go to a different screen. Now for you, what you're going to be given is graph paper. Let me give you an example. You won't be allowed to use GeoGebra on the exam at all, period. So you'll be using something like this. Now, is your own graph paper, and you basically say, okay, I've got to draw Cartesian plane. I'm going to draw it right here. I'm going to draw it right here. So let's find the point 0 and 3. So 0, 3. Our first point is 0 and 3. So the x value is 0. Remember, this is my x-axis and this is my y-axis. So 0, and then I go up 3 for the y. 1, 2, 3. So right there is my point. I'll choose, I don't know what color would be good for this. Maybe red, why not? So there's my point 0, 3. So let's do my other point 1 and 1. So I find 1, here's 1, and I go up 1. That's my second point. And my third point is 2 and minus 1. So I go over 1, 2, and go down minus 1. And now, of course, I don't have perfect graph paper, but I'm going to try to draw a line through them. And yeah, that's pretty much a straight line. Now, if you use GeoGebra, you can see immediately, and you can't really use GeoGebra, but we're going to use it just, I'm going to use it just so you can see. We're going to input the point 0, 3, and it does it for us. Then I'm going to input the point 1 and 1, maybe, 1 and 1, and it plots it. And then I'm going to input the point 2 and minus 1, and we can immediately see that the straight line, that the straight line, I don't know what I'm doing here. I added an extra point accidentally. But my line, starting here and ending here, definitely goes through all three of those points. But remember, you're not going to be able to do that. I want to sketch. And this is the thing. I will actually want to see a sketch. And I want to see it on your paper. This is the temptation for the exam. Will be able to use computational tools that I don't want you to use, because then the computer's doing the work. Now, I'll be happy to give the computer your grade, but you want to earn your grade. Ooh, that's not what I use. That's not what I use. That's what I use. No, that's not what I use either. Seriously? Everyone said, choose this, choose that. Heck with it. I know a way to get back. Can I do it? Oh, that's hideous. We may be stuck with this. Yeah, I guess that's fine. That is my background, right? That's the familiar background. Well, not quite, but we can live with that, right? We can live with that. So let's do another one. So now let's do y is equal to minus 3x minus 2. So y is equal to minus 3x minus 2. So y, I don't want to use red, is equal to minus 3x. Let me just look right here, minus 2. So again, we're going to make a table of values. Now I'm going to show you a way to do something a little bit different this time. So this is going to be my x, and this is going to be my y. Now this little cool trick I'm getting ready to show you doesn't always work. It would have worked on the first one. And we're going to do 3 points, but in an exam you might want to get 2 real fast points. And if you have time, you can go back and check. So the points we want to choose are always going to be the easiest possible choices. Kitty corner zeros. Now down here, this is just going to be an extra thing we do to check. So this says, given my equation, plug in 0 for x and see what I get. Well, y is equal to minus 2. So I immediately get a value of 0 and minus 2. So this is kitty corner zeros. The next says start with your equation y is equal to minus 3x minus 2, but plug in 0 for y and solve for x. So I have 0 is equal to minus 3x minus 2. So I'm going to move 2 to the other side. So I get 2 is equal to minus 3x. So finally, the end answer is going to be obtained by dividing both sides by minus 3. So minus 2/3 is equal to x. Now the problem with this is, I don't have a whole number here. I'm going to have to eyeball where 2/3 is. But this is still points. This is still 2 points. Minus 2/3 and 0. So let's use one more technique because we want yet another point. So in this case, what I'm going to say is choose any large value of x, or equivalently choose any large value of y, but that choice is going to have to be more carefully thought out because it could lead to a fraction. It's not going to lead to a fraction if I choose x is equal to 5. So let's show you that. So we have y is equal to minus 3x minus 2. So I'm going to let x be 5. You could let it be minus 5 if you want. I didn't. You get to choose. The point is you get to choose exactly a value of x or a value of y, and whatever your choice is, you have to find the other pair. So y is equal to minus 15 minus 2. So y is equal to minus 17. Minus 17. So there are your 3 points, 5 and minus 17. There are literally an infinite number of choices and an infinite number of points because a line is made up of all of the pairs x and y that make its equation true, and there's an infinite number of pairs of x and y, and that means you get to choose. So again, when you make your this whole method is called, again, the table of values. So you get to choose one or the other. We chose the 0 And then we chose the 0. We computed minus 2. We chose y is equal to 0. We computed minus 2/3 for x. We chose x is equal to 5 and computed minus 17 is equal to y. So let's try to graph it. So here we'll be a little bit more careful. So that's good, and if you want your y value or your y-axis to be a different color, you can. So it's my x, that's my y. So let's plot 0 and minus 2. So remember, this is x comma y. So x is 0, so I go down minus 1, minus 2. So right there is that point, 0 minus 2. Now let's go 5 and minus 17. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Was it right there? Yeah, 17. And let's draw a line through it. So clearly it's going to be a straight line. So the question is, when it intersects y equals to 0, that means it's going to intersect the x-axis. Is that minus 2/3? Yeah, it looks like it right there because this line is minus 1, and minus 2/3 is close to 1. So again, you could check it at home if you have GeoGebra and see. And the last one we're going to do, well, let's just go ahead and keep this background. So the last one we're going to do is going to be, I just have to choose darker colors. We're going to choose, I don't want to choose completely darker colors, because when I go back to my other background, we may want to see them for some odd reason. So we have y is equal to 1/3 x. So again, we make our table. In this case, always at least 2 points, preferably 3, and one is going to be x, and the other is going to be y, and what I suggested is kitty corner zeros. And then choose something else for x, since x is going to, or y, but I'm going to choose x. Since x is divided by 3, I'm going to choose x to be equal to 9. So here's an example where the kitty corner x's aren't going to help us, but we're going to find that out. Usually they do, but in this case they won't. So I'm going to compute, I've been given x, I'm going to compute y. So y is equal to 1/3, x is equal to 0. So 1/3 times 0 is equal to 0. So I was given x, I computed 0 for y. So that gives me the point 0, 0. So this line goes through the origin. Now let's try the other one. I'm given y. Y is equal to 0. I want to compute x. Well, I have a denominator, so I'll multiply both sides through by 3. Three times 0 is 0, so 0 is equal to x, because 3 times 1/3 is 1. So I get the exact same point. So I didn't help. It turned out that using my kitty corner method I did not get two distinct points. That's always the case when you don't have a constant term, where your ax plus by is equal to c, where your c is equal to 0. But lots of times you have a constant term. So anyway, this is a line that goes to the origin, so I absolutely have to have this last point here. In the last point, I'm given x, so I want to compute y. So y is equal to 1/3 times 9. So y is 9 divided by 3, so y is equal to 3. So 9 and 3. So let's at least plot 9 and 3. Again, I'm going to try to draw a Cartesian plane. I'm going to make this as thin as I can, the line. I may have made it too thin. Let's go with that. Go dark, grab. There. Don't like it. I'm going to redo it. I want to get right on top of it. Okay, good enough. Much better than before, right? So 0, 0 is easy to point. That easy to plot. That is a point lying on the origin. Right there. That's 0, 0. Now I want to go 9 and 3. So I go in the x direction, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then up 3. There's 1, 2, 3. So I'm going in the positive direction, 3. And now I can draw my line between those 2 points. Well, as you can see, not the best drawing of a line between 2 points. I'm fine if I actually start at a point. You can just imagine. So there you go. We just plotted with a lot of problems, so it seems. Notice here I give you the sheet. This is much better because each one of these little bitty squares, if you can see them with the screen feed, is 1 unit. So that's 1, 2, 3, 4, 5. So now we're going to graph nonlinear equations. So remember, the graph of any equation in the variables x and y are simply the values of x and y that make it true. So we're going to graph y is equal to x squared. So let's come over here. Actually, I'm kind of liking that. There. I'm going to use that space. I'm going to use that for this next. I'll make this big. Turn it into an eraser. Uh-oh. I want to turn it into an eraser. Now make it back small. Change the color to dark. So our equation was y is equal to x squared, right? Yeah. So y is equal to x squared. That's what we want to plot. Y is equal to x squared. So the procedure here is going to be really similar. But in this case, we're going to want to do a table of many values. And in this case, we're just going to choose values of x. I'm going to do several because we want to look for a pattern. And we're going to use some things that we know about x squared. So this is going to be x, and this is going to be y. So we always want to choose x to be equal to 0. So 0 squared is equal to y, so that's 0. So I've found one point, 0, 0. and I can plot it right there. Well, let's try all just integer values. If x is equal to 1, then x squared is equal to y, so 1 times 1 is 1. So the point 1 and 1 lies also on the graph. Well, if I recall that minus a squared is equal to a squared, I'm good to go with another point. I'm going to choose minus 1 for x. So minus 1 squared is the same as 1 squared. So it's a 2 for 1. But in this case, x is minus 1 and y is 1. So I go over minus 1 on the x direction and 1 in the y direction. Let's keep on going. 2. Well, 2 squared is 4. So I get another point, 2 and 4. So x is equal to 2. 1, 2, 3, 4. And minus 2, I get 4 as well. So I go over here, minus 1, minus 2, but up 4, 1, 2, 3, 4. Let's do 3. 3 squared is 9. Minus 3 squared is also 9. So I get 2 more points, 3 and 9, and minus 3 and 9. So 3 is 1, 2, 3, and up 9. So that's 4, 5, 6, 7, 8, 9. Minus 1, minus 2, minus 3. That's 4, 5, 6, 7, 8, 9. I'm going to stop right here, and I'm going to try to freehand draw through here. It's not going to be very good. I told you it wasn't going to be very good, but we can actually go over to GeoGebra and let's see what it really does look like with GeoGebra. All you have to do is y is equal to x, and for the square you can do the up arrow square, and right there is what the real graph looks like. This is a graph of a parabola. So not all equations in two variables are lines. Let's do one other example. Oh, let's graph y is equal to the absolute value of x. You know, Control Z is always underappreciated. Although I just exceeded my number of backward steps. That's fine. So all I'm going to do is change our equation. Our equation was that y is equal to the absolute value of x. I need to erase, yeah, it's fine. So y is equal to the absolute value of x. So again, the point 0 and 0 is a point, because if, again, you just choose some values. You get to choose the x values. Let me emphasize that again. You choose x. And then you compute y. So 0, 0 is on my graph. If I choose x is equal to 1, the absolute value of 1 is 1. So the point 1 and 1 is also on my graph. Well, again, let's choose negative values. Minus 1. Well, the absolute value of minus 1 is 1. So minus 1 in the x value, 1 in the y value. 2, well, the absolute value of 2 is 2. So I go over 2 on the x and up 2. And let's do a minus 2. And I also get 2, so I've got some more points up here. So minus 2 and 2. And let's say 5. Absolute value of 5 is 5, and minus 5, and absolute value of minus 5 is 5. So I got 2 more points, 5 and 5, minus 5 and 5. So I want to graph those. So 1, 2, 3, 4, 5 on the x, 1, 2, 3, 4, 5 on the y. Minus 5. So minus 1, minus 2, minus 3, minus 4, minus 5. Up 5. 1, 2, 3, 4, and 5. Okay, so now when I draw a line through those points and another line through these points, and I'm going to indicate that that's going to go on forever in that fashion. This is the graph, what I just drew here, of y is equal to the absolute value of x. Whereas this is the graph, or part of the graph, of y is equal to x squared. Okay, that's it for section 3.1.